Here we have our group period 3 oxides. You're going across period 3, and we've talked about the previous video. We talked about some of these already, but just to summarize, you get a nice trend as you go across. As you start off with sodium on the left, and that is basic. Say magnesium is basic, and then amphoteric, and then after that, these are all acidic. So you get a bit of a trend as you go across. Let's also just see the ones that are soluble in water I've done in green. So sodium oxide, phosphorus oxide, P4O10, SO3 and SO2, they're all soluble in water. And they'll give you different pHs. Sodium will give pH 14, the others will pH 1, and SO2 gives a weak acid, so maybe pH 3 or 4. The magnesium oxide is very, very tiny bit of it dissolves, just enough to make it the hydroxide ion a bit higher and pH 9. And then aluminium oxide, silicon dioxide, both insoluble in water, but they will react. Well, aluminium oxide will react with acids and alkalis, dissolve in both of them. Silicon dioxide will dissolve in very strong alkali. So let's have a look at silicon dioxide. Now we classify it as we say it's acidic. Obviously, it can not be acidic in the Bronsted-Lowry sense because it hasn't got any protons, so it can't give away protons. But it's a Lewis acid. Okay. Now let's see what happens when we react that with water. We react that with strong alkali. Sorry. If we get SiO2 and react that with OH minus, it gives us this ion, which looks very foreign looking to us. It's called a silicate ion. Right, so to balance there, we're going to need 2 of those and water. Okay, so if you get silicon dioxide, it will dissolve in really, if you get this sodium hydroxide really concentrated, almost molten sodium hydroxide, it will start to dissolve in that. It won't, so it is acidic, but not very acidic. Right, now how does it act as a Lewis? How does it react as a Lewis acid then? Well, you've got silicon in silicon dioxide, and it is bonded to, I'll move this down a bit. You've got, the silicon will be bonded to 4 oxygens. Right, and of course that is going to make the silicon quite a partial positive charge. So it's not a strong enough Lewis acid to react with H2O. Right, the lone pair from water can't react with that. That doesn't happen. It's obviously not sufficiently acidic. But if you get OH minus, which is a better base, because it's actually negatively charged, it's not just a partial charge, that is strong enough to react, to act as this is acting as a Lewis base. The lone pair will go to the silicon. That's how the reaction starts off. Okay, let's just have a look at this silicate ion, which does look a bit, we've not come across it before, but if we just think about, well, what silicon is just below carbon in group 4. So if we think of this ion, the CO3 2- ion, that is very familiar. That's obviously the carbonate ion. So the silicate ion is, analogous to the carbonate ion, if you remember it that way. Right. Let's and again, just I think I've said before, but if you just contrast the difference between carbon dioxide, which is a simple covalent molecule, CO2. Superficially, SiO2 looks like it's got the same formula, but it's really different because it forms a giant covalent structure, because it forms 4 single bonds rather than 2 double bonds. And that means that the network of covalent bonds can carry on, and means silicon dioxide is a very abundant element, silicon, and it makes up most of the rocks or SiO2. Whereas carbon dioxide, you don't find it in the ground, it's all in the air because it's a gas, because it's a simple covalent molecule with a low boiling point. Right, let's now move on to phosphorus. And so phosphorus, P4O10, and SO3. So P4O10, again, it is a Lewis acid. Why is it going to be a Lewis acid? Well, it reacts with water because, I think we looked at each phosphorus in P4O10 is forming one double bond and 3 single bonds. So you're going to have a big, oxygen is an electronegative element. You have a big partial charge on the phosphorus. It's more, and it is more acidic than the SiO2. This will react with water. SiO2 won't react with water. Water is the lone pair is going to attack that phosphorus. That's what's going to start off the reaction. Right, if you react P4O10 with water, it reacts very, very readily with water, and it will form phosphoric acid. So let's write down the equation for that. Here we've got P4O10, going to react with water. Phosphoric acid is H3PO4, and that's a strong acid, so you're going to get a pH of 0 or 1. Right, we've got to balance that, so we're going to have to put a 4 in front of that. Then that means we've got 12 hydrogens here, so we're going to have to 4 times 12, so we're going to have to put a 6 there. Just check the oxygens are okay. We've got 10 there and 6 there, that's 16. We've got 4 times lots of 4, 16 there, so that's balanced. Okay, so that is the equation of that. Right, now we need to think, right, this is a tribasic acid, so what would be the salt formed with if you reacted phosphoric acid with sodium hydroxide? Well, it would be H3PO4 NaOH. Sodium forms a 1+ ion, so the formula of so the phosphate ion, because it's H3PO4, the phosphate ion must be 3-. Yeah, it is. It's actually got a double bond to the oxygen and 3. You may remember from your structure of DNA, and 3 negative charges. Okay, so the formula is going to be Na3PO4 sodium phosphate. Okay, to balance that, I want a 3 there, and then I want 3 H2Os. This is the salt. Okay. Now, the reason why I'm mentioning this is because very often they will ask you what will happen if phosphorus oxide, P4O10, reacts with NaOH. Now, what we get is we get P4O10 is an acid, isn't it? It's a Lewis acid. H3PO4 is a Bronsted-Lowry acid. But you get the same salt in each case. So the salt you're going to get, the formula of the salt is going to be Na3PO4. And let's see, and you're going to get some water as well. So we need to balance that. Well, we need to put a 4 in front of that, which means we need 12 NaOHs. And how many waters are we going to get out of that? Well, we've got 12 hydrogens, so we're going to get 6 waters. Just check all the oxygens are okay. We've got 16. We've got 4 times 4, that's 16 there, plus 6 there, that makes 22. And we've got 10 there and 12 there, it's 22 on that side as well. So it's okay. So they always ask that question. And I always, what salt are you going to get from P4O10? Well, just think, what salt would you get from phosphoric acid? And it's the same formula. You could even have well, this equation. So there we've got where does NaOH come from? Well, we get NaOH by reacting Na2O with water. So let's just see what happens if we've got P4O10 and Na2O. That's a base, so a Lewis acid here with a base. You would get the same, you get Na3PO4. We would have to balance that, put a 4 there. So that means we need 12 sodium, so we need 6 there. You see the oxygens are all balanced there, and you don't get any water in that case. So you get the same salt by reacting P4O10 with the sodium oxide. It's always the same salt. Right. Okay, let's look at SO3, and that is you'll see how similar that is to P4O10. So SO3, right, that reacts with water to form sulfuric acid. So SO3 plus H2O is going to give us H2SO4, and that equation is balanced. What makes the water react with sulfur dioxide? Well, you've got lots of electronegative oxygens. That's going to make this sulfur quite delta positive. That means it's a Lewis acid. It can react with H2O molecules because you've got lone pair on the water there. And this is pretty delta positive, so it can react with H2O. Remember the case we said with silicon? Silicon can't react with H2O. You need a stronger base, you need OH minus, because with the silicon you mustn't have such a strong delta positive on the silicon atom as you do on the sulfur atom. So SO3 is a Lewis acid, sorry. Pretty good at accepting lone pairs of electrons. Right, so that is sulfuric acid. Now let's see what salt would we get if you react sulfuric acid with NaOH. So you get NaOH plus H2SO4. Well, we all know the sulfate ion has got a charge of 2 minus, so the salt's going to be Na2SO4, and we're going to get 2 water molecules. We're going to put a 2 there. We get 2 H2O. So that's the salt we get if we add, this is a Bronsted-Lowry acid. What would you get if you reacted the Lewis acid with a base? Well, you get the same formula of the salt, so let's write that down. You would get SO3 plus NaOH would give you Na2SO4, and you get some H2O. What we need to do to balance that? Well, we need 2 sodium, so we need a 2 there, and you just get 1 H2O. So that would be the if you reacted the Lewis acid with NaOH. And let's take it one step further. Let's say we do SO3, this time not with NaOH, but where do you get NaOH from? Well, we react Na2O with water. So let's react those together. What you get sodium sulfate, and in that case, you don't get any water. Right, just to wrap this up then. So again, they really do ask an awful lot. These salts, which where you get Lewis acid, not the Bronsted-Lowry acid, just the oxide reacting to form a salt. So you've got to realize it's going to be the same formula as if you use the Bronsted-Lowry acid. Right, actually, let's just do one more before we do that, because they've asked it a few times. They said, what are you going to get if you get magnesium oxide, a basic oxide, and you react it with P4O10, which is a Lewis acid? What are you going to get? You're going to get a salt, but what's going to be the formula of the salt? Well, magnesium forms Mg2 plus ions. P4O10 will give you H3PO4, phosphoric acid, won't it? So that means the PO4 ion in the salt is 3 minus. So what's going to be the formula of magnesium phosphate? It's going to be Mg3, sorry, PO4 twice. So let's balance that. So we need to put a 3 there. No, we don't, because we're going to have, right. We've got 4 phosphoruses here. We've only got 2 on this side, so we have to put a big 2 in front there. So that means we've got 6 magnesium atoms, so I need to put a 6 in front of that. And then we've got 16 oxygens on this side. Let's just check. 6 there, 10 there, 16. And how many have we got on this side? We've got 2 times 8 there, but there's 2 there, so 16 on that side, so it's all balanced. So they have asked that one a few times. Okay, the key again is to remember the Lewis acid. Just pretend that you're dealing with the Bronsted-Lowry acid, and it's quite easy to imagine what the formula of the salt would be then. Right, let's finish up with silicon dioxide. I'm not going to say very much about that. Sorry, not silicon dioxide, sulfur dioxide. Right, sulfur dioxide is SO2. It's actually got a lone pair on the sulfur there, so that would be a bent molecule. You might this angle here would be, well, there's 3 bonding pairs, and the 3 pairs, sorry, one of which is, so that would give you trigonal planar. But one of them would have you get more repulsion from this, so that would be slightly less than 120, the bond angle there. And also interestingly, this molecule would have a dipole because it's asymmetrical. Whereas if you look at sulfur trioxide, that wouldn't have a dipole because there's no lone pairs there. It's perfectly symmetrical, and those bond angles would all be exactly 120. They wouldn't, yeah. Right. Let's think which would be the strongest acid. Well, we'd probably say this would be the strongest acid, Lewis acid, because you've got a bigger delta positive on the sulfur there, because it's attached to 3 oxygens, whereas this one is only attached to 2. And that's kind of borne out when you react these to make the Bronsted-Lowry acid. So you get SO3 and H2O goes to sulfuric acid, whereas we do SO2 and H2O, you get H2SO3, which is called sulfuric 4 acid, or sometimes sulfurous acid. And this is a weak acid. This is a weak Bronsted-Lowry acid. And this is a strong, this completely dissociates. And this is a reflection of this, you know, this would be, which would be the strongest Lewis acid out of these 2 structures, you know. The strongest Lewis acid you predict would be this SO3, and that gives rise to the strongest Bronsted-Lowry acid. So if you get H2SO3, it looks like it's a dibasic acid, but of course it's only a weak acid, so it's not really. It's like what's going to happen is you're going to get H2SO3 is only going to lose 1 proton, unless it's a very alkaline solution that you put it into. So you're going to get HSO3 minus, hydrogen sulfite ion, and H plus, and of course that's an equilibrium because it's a weak acid. Okay, so that is the end of that topic.